Hi, my name is Alex. I'm currently a graduate student at MIT, advised by Larry Guth. And I'm graduating this spring, and I'm going to start as an assistant professor at NYU in fall 2025. So I want to tell you about some recent work with Cosmin Pahota and Dmitry Zakharov about discrete geometry. So, uh, our main theorem takes place in discrete geometry, and it's an extremal problem because it's about worst case scenarios. But in order to address this extremal problem, we bring in tools from harmonic analysis and fractal geometry. And so that's kind of my favorite part of this area is the interaction between extremal problems in combinatorics and analytical methods coming from harmonic analysis and fractal geometry. So that's the connection that I want to tell you about. Okay, so to start with, I'll just say what the main problem is. So the setup is we're going to have n points inside the unit square. So those are these points, P1, P2, etc. And we're going to place a delta-wide tube through each point. And when I say place a delta tube through the point, I mean the central line has to go through that point. Okay. So when we do this, we have a collection of n points and a collection of n tubes. And we say there exists an extra incidence if there's some point lying on a tube where it's not the tube belonging to that point. So for example, we have this tube T3 over here, and it belongs to the point P3. But there's also this tube T2, which goes through the point P3. And so P3 lying on T2 is an extra incidence because it's not the tube that P3 belongs to. Okay. And the question we're interested in is how big does n need to be to guarantee that there exists some extra incidence? So an easy upper bound is that if n is bigger than delta to the minus 2, then there exists some extra incidence. The reason is that there has to be 2 points that have distance less than delta from each other. So any tube passing through one of those points has to also contain the other one. On the other hand, we can construct a configuration of delta to the minus 1 many point tube pairs with no extra incidence. So in this example, we arrange the points so that the spacing between them is delta, and then we put a vertical delta tube through each point, and those tubes won't go through any extra points. So the true answer to our question lies somewhere in the range from delta to the minus 1 to delta to the minus 2. And so actually, we first wrote down this question because we realized it was connected to a different question we were interested in, and I'll get to that later. When we wrote it down, we wrote down this easy upper bound, wrote down the easy lower bound, and we didn't really know what the true answer was. And we couldn't find any prior literature on this problem. Okay. The main theorem we proved is that if there are greater than delta to the minus 3 halves points, this minus little o of 1 means it has to be greater than delta to the minus 3 halves by a significant amount. If there's greater than delta to the minus 3 halves points, then there exists some extra incidence. So this is a non-trivial theorem because it improves on the easy bound from the last slide. And it kind of splits the difference between the easy upper bound of delta to the minus 2 and the easy lower bound of delta to the minus 1. Okay. So the reason that we got interested in this question about extra incidences is because of a connection to a problem about triangles. So this is called Heilbronn's triangle problem. And Heilbronn's triangle problem asks the following. We're going to define a quantity delta of n to be the smallest number such that in any set of endpoints, there exists some triangle with area less than or equal to delta of n. Okay, so this is an extremal problem because it's about the worst case scenario over an arbitrary set of endpoints. And so the main question is to prove asymptotic upper bounds for delta of n, which amounts to taking an arbitrary set of points and somehow analyzing it to find a small area triangle inside of it. Okay, so there's an easy upper bound for this problem as well. to see this, take the set of endpoints and split it into n over 5 many strips. Okay, by the pigeonhole principle, some strip has to have at least 3 points, and some triangle contained entirely in one strip, just by connecting some 3 points in one strip, has to have area less than 5 over n, because that's the area of the strip. So that's an easy bound for this problem, and you can see that it has the feature that it works for an arbitrary set of points, no matter how they're arranged. Okay, so the easy bound is 1 over n. And it was an open question for a while to even improve over this easy bound. And in 1951, Roth proved that there exist triangles with asymptotically smaller area than 1 over n. So in particular, he improved by a factor of log of n to the minus 1/2. Okay, so then 20 years later, Schmidt worked on this problem, and he gave a simpler argument, which shaved one of the logs off of Roth's theorem. And Roth was somehow inspired by Schmidt's paper, and he came back to this problem, and in a really important breakthrough work, he proved that there exist triangles with area less than n to the minus 1.1. This is a power-saving bound, and it's a really big improvement over what came before. This paper also introduced the analytical method that is kind of the basis for all subsequent work, including ours. I'll also mention that Roth kind of got obsessed with this problem, and he wrote not one, but around 4 papers developing his method and getting better and better exponents. And in 1981, Komlos, Pintz, and Samaretti worked on this, and they kind of sharpened Roth's method to get the bound n to the minus 8 over 7. Okay, so this is the problem we were working on, and a couple of years ago, we improved Komlos, Pintz, and Samaretti's bound by a little bit. So we improved n to the minus 8 over 7 to n to the minus 8 over 7 minus 1 over 2000. And it was through that work that we sort of realized the connection between this triangle problem and harmonic analysis and fractal geometry, and got interested in developing that connection further. And a corollary of our main theorem is a new bound for Heilbronn's triangle problem. And the new bound is delta of n is less than n to the minus 7 over 6, plus a little bit. So this is a new bound that significantly improves on our bound from a couple of years ago. And it's a different framework from our bound from last year. Okay. So the proof of the triangle result using the extra incidence result is pretty simple. So I want to just give it in full. So here's how we find small area triangles. Take your arbitrary set of endpoints and form around n over 4 pairs of points at distance less than, say, 5 over root n from each other. Okay? This is always possible because in any set of endpoints, by the pigeonhole principle, there's some 5 over root n by 5 over root n grid that has to contain 2 points. So there exists some pair of points at distance less than 5 over root n. And so we just find one pair that has that distance, remove it, and keep iterating that until we have lots of disjoint pairs at distance less than 5 over root n. Okay? For each pair, we make a delta tube through that pair, meaning that it's the delta neighborhood of the line passing through the pair of points. And now, if we have a collection of n points, or n over 4 points, by just selecting an arbitrary point from each of the pairs to serve as the base point, and a tube through each of those points. Okay. If we choose delta to be a little bit bigger than n to the minus 2/3, then due to that choice, the number of point tube pairs is bigger than delta to the minus 3/2. And our theorem implies that there exists some extra incidence. And an extra incidence is exactly a third point in one of these tubes. So we can compute the area of this triangle using the formula area equals base times height. And the base of that triangle is n to the minus 1/2. That's how far apart our pairs were. And the height is less than n to the minus 2/3 because that's the numerology of our extra incidence theorem. So the area of the triangle is n to the minus 7/6 as desired. Okay. So this type of argument fits into a general setup. The general setup is you have some set of points inside the unit square, and you have some set of delta tubes, and the quantity of interest is the number of incidences between the points and tubes. And so an incidence is a point-tube pair where the point lies on the tube. And it's known that lots of problems in combinatorics and analysis are related to proving upper bounds for incidences. So there's lots of problems such as, for instance, the sum product phenomenon or the Kakeya set problem, where you're interested in something that doesn't necessarily on the face of it have to do with incidences, but then you can perform some manipulations and say that if you can prove an upper bound for the number of incidences between some special configuration of points and tubes, that would correspond to a good bound for the problem you started with. And what we learned from Heilbronn's problem, and we're starting to find in general, is that there is kind of a little zoo of problems that are related to proving lower bounds for incidences. So this is a slightly different setting where the points and tubes are going to have some kind of relationship with each other. And the goal is to use that relationship to prove a lower bound for the number of incidences. So these are the incidence problems that we're now interested in. Okay. So that's kind of the general context. And moving back to this specific problem, the extra incidence problem from the first slide has a nice advantage over the triangle problem that we worked on a few years ago. The advantage has to do with symmetries. So the extra incidence problem is invariant under a large family of symmetries. So to explain this, let me maybe start with the triangle problem. So one observation that Roth had is that when you're trying to find a small area triangle, what you can do is take some subsquare inside the unit square and look at it and see that if there's a very large density of points there, you could just zoom into that subsquare and find a large triangle there. And so then you're allowed to assume that every subsquare does not have such a large density of points, otherwise you would just zoom in there. And that hypothesis is somehow useful in the analysis. And we get an upgraded version of that observation for the point tube problem. If for any rectangle, any U by W rectangle, we say a point tube pair lies in that rectangle, if the point lies in the rectangle and the tube passes through the short ends, but not the long ends of that rectangle, which imposes a slope condition on the tubes that they are somehow aligned with the slope of the rectangle. So this is the appropriate generalization of a pair lying in a rectangle. Okay. And if we take a rectangle and we apply an affine map to map it to the unit square, then any point tube pair lying in the rectangle, according to the definition I just said, gets mapped to a point tube pair in the unit square. And the slope condition on the tubes means that the new tubes in the new configuration will have a significantly larger width. So if there's any rectangle that has an overabundance of point tube pairs, we could find a new configuration with a large number of point tube pairs and even thicker tubes. Okay, so this leads to a dichotomy. Either the point tube pairs are well spread out among all rectangles, and we can use that in the analysis, or there's some point tube pair that has an extra concentration, and we can just zoom in and look for an extra incidence there. And it's a stronger piece of information that the point and tube pairs are spread out among all rectangles compared to just knowing the points are spread out among all squares. This is a really important step in our paper to move from analyzing concentration over squares to analyzing concentration over rectangles. Okay, so the theorem we prove is that if you have any collection of point tube pairs and they're spread out over rectangles in some quantitative sense, then the number of incidences is at least the expected number of incidences if all the points and tubes were placed uniformly at random. The expected number of incidences is this quantity delta times number of points times number of tubes, because each point is a set of area delta. And so if the points are placed randomly, there's, size of p many points, and each one has a delta chance to land in that tube. So this right-hand side is the expected number of incidences if things are placed uniformly at random. Okay, so this is the theorem that we work hard to prove. And we use this theorem to prove the extra incidence theorem I mentioned before. So the connection is that this theorem, it has a stronger hypothesis because we require that the point tube pairs are spread out over rectangles and they're not just an arbitrary set. But it also has a stronger conclusion because the conclusion is a very large lower bound of the number of incidences, not just the existence of some extra incidence. And this is a stronger conclusion that's easier to analyze. That's often the case in analysis, that it's easier to prove some quantity is near its expected value rather than just to prove it's greater than zero. In some way, we're searching for hay in a haystack rather than a needle in a haystack with regard to incidences. Okay, and this theorem is combined with the rescaling idea in order to prove the extra incidence theorem from before. Okay. In order to prove this theorem, we use a two-step strategy, and it's a two-step strategy that we learned from Roth. So we define a multi-scale incidence quantity, I of WPL, which is the number of point line pairs where the distance between the point and the line is less than W. Okay, so if we plug in delta, then this is just the number of incidences between the points and the tubes. And if we plug in a larger number, it's the number of incidences between points and thickened tubes. So the first step of the strategy is to prove that if we take some very large initial scale, Wi, and we look at this normalized incidence count, which is expected to be around 1 if everything is placed randomly, then this normalized incidence count is pretty large at that initial scale. And the second step is an inductive step where we prove that the number of incidences, this normalized incidence count doesn't change very much between the initial and final scale. And this inductive step uses the high-low inequality, which is an inequality from harmonic analysis that was introduced by Guth, Solomon, and Wang a few years ago in the context of upper bounds for incidences. But actually, Roth proved something very similar to this inequality in his 1971 paper, and he used it in his two-step strategy for finding triangles. So Roth's paper is, in a way, a predecessor to the high-low inequality. And that's really the driving force of the method, is this method for comparing the normalized incidence count at a large scale to the normalized incidence count at a small scale. Okay. So in order to apply this strategy, we don't just apply it in the entire unit square. Instead, we zoom into a rectangle and apply this strategy there. The challenge is that it's easy to find some rectangles which satisfy the initial step 1 and others that satisfy the inductive step 2, but it's hard to find rectangles that satisfy both 1 and 2. So draw a picture, right? This blue square over here, that's an example of a rectangle, and maybe we can prove the inductive step will work for that rectangle. And maybe this skewed rectangle over here is some different rectangle, and we can prove that it satisfies an initial estimate, but not the inductive step. But what we need is a rectangle that satisfies both 1 and 2. And these are hard to find. So the bulk of our paper is finding rectangles that satisfy both these properties. And in order to do that, we need to really carefully analyze how our point tube pairs are distributed over rectangles. So we introduce a branching function, which is a function of 3 variables, f of x, y, z, which captures a lot of geometric information about how the points in tubes are spread out over rectangles. So this builds on a line of work in fractal geometry, including people like Borgen and Coletti and Schmerkin and many others, of using functions to characterize how point sets concentrate in different places. And it's a new ingredient to introduce this branching function of several variables to analyze how points in tubes concentrate in their joint phase space. So we convert basic geometric information about rectangles and how they interact with each other into algebraic information about this branching function. And then we phrase 1 and 2 also information about the branching function. And in doing this, we convert our geometry problem into an algebra or analysis problem about analyzing a function. So the picture is that there's some red set in the parameter space. There's a two-dimensional parameter space of rectangles, their width and their aspect ratio. And there's some subset of this parameter space that satisfies the initial estimate, property 1, and some subset that satisfies the inductive step, property 2. And we work hard and analyze this function in order to find that these two sets intersect. And that's kind of the goal. And this turns out to be quite a delicate analysis. But I think part of what I'm excited about is that this branching function framework is a really flexible and powerful way to analyze sets of points and tubes in the unit square. And so I think it'll have some relevance for other incidence problems, and that's something that we're working on right now. Okay, thank you.